You are given an array of numbers in a limit k, and you need to find the longest stretch of consecutive elements where no single value repeats more than k times within that stretch. In other words, count how long a run of numbers can get before some value shows up too many times. Return the length of that longest valid stretch. One tiny mistake here, using an if instead of a while, silently gives you the wrong answer on almost every real input. We want the longest stretch of messages where no emoji shows up more than k times. Live as messages stream in. Hey, I'm Kai and welcome back to Fun with Learning Technology. Today we are solving longest subarray with frequency at most k. This looks like it needs some fancy heap or sorting trick. It doesn't. By the end you will spot this pattern in seconds. This exact shape, longest run, where nothing repeats too much, powers rate limiters and spam filters in real systems. Get this pattern down once and you'll reuse it constantly. Take this row 1, 2, 3, 1, 2, 3, 1, 2 with k equal to 2. The first 6 values form a good stretch. Each value shows up at most twice. Add a 7th and something breaks. We just need 3 things. A dictionary that maps each value to how many times it's currently in our window, a left and right pointer marking the window's edges, and one variable tracking the best length so far. Try it the obvious way, pick start 0, end 7, count all 8 values from scratch just to check one window. Now repeat that recount for every one of the 36 possible start-end pairs in this tiny 8-item array. That's the plan that falls apart as the stream grows. Here's the problem, when we move the window by 1, almost nothing changed, yet we recount everything. We already knew the old counts, we just threw that work away. That's the real waste, not the comparing itself. Instead, keep 2 pointers, a left edge and a right edge of a window. Push the right edge forward, adding one new value at a time. The window only shrinks from the left when a value's count goes over k. We keep a dictionary called counts. When a value enters the window, we bump its count by 1. That gives us an instant lookup instead of rescanning the whole window every step. Take this array and k equals 2. The window grows, 1, 2 copies of this value, still fine. A third copy shows up. Now we shrink from the left until we're legal again. Track the biggest window size we ever reached along the way. In short, the window only ever moves forward, and the dictionary tells us instantly when we've broken the rule. That's the whole idea. Every element enters the window exactly once. Every element leaves the window at most once. So the whole pass is linear, not quadratic. Even though shrinking looks like it could cost as much as brute force, it doesn't. Pointers only ever move forward. That drops us to big O of n. Clean. Here's the algorithm in plain steps. Add the value at the right pointer, increment its count. If that count is now over k, shrink from the left, dropping counts until it's legal again. Then update our best length using the current window size. We start with an empty counts dictionary, left at 0 and best at 0. Left tracks the window's left edge, right will just be our loop index. For every value at position right, we bump its count. While that count is over k, we remove the value at the left pointer from counts and move left forward, shrinking until legal again. After each shrink, the window is legal, so we compute its size, right minus left plus 1, and keep the bigger of that and our current best. Here's the whole thing together. Every line already explained. Growing window, dictionary counts, and a running max. With k equal to 1, as soon as we see 1, 2, 1, the second one pushes count over the limit, so left shrinks past the first one. The window size never beats 2, matching the expected answer. Pause for a second. What does this return for 7 5s with k equal to 4? Drop your guess in the comments before I show you the answer. The answer is 4. Once the count of 5 hits 5, we shrink from the left until we are back down to 4. The window can never grow past that. A common slip, shrinking with an if instead of a while. If duplicates pile up fast, one shrink step might not be enough to get legal again. You need to keep shrinking until it actually is. The brute force approach still works. Just check every subarray and recount frequencies. It's simple to write, but it's quadratic at best. Way too slow once the stream gets long. Our sliding window solution runs in big O of n time, since each element is added and removed at most once. Space is big O of n for the counts dictionary in the worst case. Strip away the emoji counting, and K, and what's left is a pattern. Whenever you need the longest or shortest stretch that stays under some running rule, reach for 2 pointers and a count map that only ever grows and shrinks, never restarts. That's rate limiters, spam filters, anomaly windows, and this problem, all the same trick wearing different clothes. Small channel, honest ask, one follow. That's it. We took the frequency cap problem, used the growing window with the dictionary for instant counts, and got a linear one-pass solution. Remember that brute force recount that broke down? This is exactly why we didn't need it. The takeaway, whenever you need the longest or shortest stretch under some running constraint, reach for 2 pointers and a count map before anything fancier. Small channel, honest ask, one follow, that's it. If something feels off or missing, or you want to see something new, tell me in the comments. Quick one. Array of 8 elements, k equals 2. What's the largest window we can grow to? Pause and take a guess. Think it through for a second. There's no fixed answer. It depends on how the values repeat. Since the window only shrinks when one value's count exceeds k. Here's the trickier one. Why do we need a count dictionary instead of just a set of scene values? Guess before I answer. Give it a moment. A set can't tell you if a value appeared once or 5 times. We need the exact count to know exactly when to shrink the window.